Hello everyone, my name is Oleg Pankevich. I am a solution engineer at StarWind. I hope you hear me well and can see the screen with the webinar's title. We have noticed that many customers often choose storage drives for the new environment or upgrade existing one based on marketing advertisements or outdated information. In such case, the resulting solution may be an overkill, not cost-efficient, or even low-performing. Today we will talk about modern storage media for small and medium environments. In the beginning, I will highlight major improvements in 2019, what we can expect in 2020 related to storage devices. After that, we will have an overview of storage media and price comparison. As conclusion, I share the recommendation prepared by our team, what drives to use and for what purposes. Finally, I would be happy to announce new model lines of StarWind hyperconverged appliances. You can write a question in chat window or on question window, and I will answer them during the presentation or in the end of webinar. So let's start. 2019 was not rich on news in storage world, but still there are some interesting points. PCI Express 4.0 is released. The PCI Express 4.0 bus delivers up to 32 GB second per 16 lanes, what doubles 16 GB second maximum of PCIe Generation 3. It means that default NVMe drive with 4 lanes may have approximately 7.5 GB second throughput. Only AMD CPUs support this protocol right now, and there is no clear information when Intel will add it. I hope we will see PCI Express 4.0 in coming Cooper Lake microarchitectures this year. As for the drives, Kioxia, former Toshiba, has started shipment of fast data center grade PCI 4 NVMe drives a couple of days ago. I am talking about Kioxia CM6 and CD6 drives. The second news is bounded to previous, and it is a publishing of PCI Express 5 specification. It doubles the bandwidth of PCI Express 4, so we can get up to 64 GB second per 16 lanes. Certainly, there are no any compatible hardware right now, and I personally doubt that we get any in 2020. Next news is Intel Optane persistent memory. Intel Optane is an innovative new solution that will move larger amounts of data closer to the CPU, so it can be accessed, processed, and analyzed in real time without first being retrieved from storage. It is comparable to DDR4 DRAM at low latencies. Additionally, it will have higher capacity and data persistent feature typically found in NAND SSDs. Intel Optane persistent memory models have the form factor of DDR4 DIMM and capacity from 128 GB to 512 GB. Using persistent memory for ordinary infrastructure services in SMB is questionable right now because of high prices and low new advantages in compared to NVMe or SSD drives. The last but not the least is production-ready 16 terabytes spindle drives and sample shipments of Western Digital 20 terabytes drives with partial microwave-assisted magnetic recording technology implementation, which eliminates density limitation of perpendicular magnetic recording. With 20 terabyte drives, one 2-unit chassis reaches around 350 terabytes usable capacity. Modern storage media for data centers is divided in two branches depending on type. Hard disk drives or spindle drives are non-volatile data storage devices. Hard disk drives first appeared in 50s years of previous century. Rapid advancement in technology led to increase in capacity by orders of magnitude so that modern hard disk drives are able to store up to 20 terabytes of data with price as low as 3 cents per gigabyte. Serious disadvantage of hard disk drives is that their operation relies on mechanical principles. Actually, spindle drives is the last of devices in computer world which is not based on purely electronical or electrical phenomena. Hard disk drive stores information in magnetic form on the surface of platter. It is covered with thin layer of ferromagnetic material and is perfectly polished. To increase spindle drive's capacity, each platter has two magnetic surfaces, and a group of identical platters is mounted together to form platter assembly. Maximal number of platters in assembly depends on disk, form factor, and height. All platters are mounted on a single spindle and are synchronously rotated with fixed speed. Once hardened HDD is powered on, electrical motor spins up platter assembly to nominal speed, and this rotation continues until HDD is powered down or goes into power saving mode. This speed, which is called rotational speed, is measured in revolutions per minute, or RPM, and makes significant effect on both sequential and random access performance. Read and write are performed by magnetic heads, one head per platter surface. Today you can find on market 3.5 inches 7200 RPM NLSAS or SATA drives and 10 or 15K 2.5 inches SAS drives. 15K SAS drives are not so popular because of high price, but are still in use. The second branch is flash or solid-state drives. Flash uses semiconductor chips, not magnetic media, to store data which is saved to a pool of NAND flash. NAND itself is made up of what are called floating gate transistors. Unlike the transistor designs used in dynamic RAM, which must be refreshed multiple times per second, NAND flash is designed to retain its charged state even when not powered up. This makes NAND a type of non-volatile memory. One of the functional limitations of solid-state drives is when they can read and write data very quickly to an MP drive, overwriting data is much slower. This is because while flash read data at the page level and can write at the page level, assuming surrounding cells are empty, they can only erase data at the block level. This is because the act of erasing NAND flash requires a high amount of voltage. While we can theoretically erase NAND at the page level, the amount of voltage required stresses the individual cells around, and the cells can be rewritten. Erasing data at the block level helps mitigate this problem. The only way for flash drives to update an existing page is to copy the contents of the entire block into memory, erase the block, and then write the contents of the old block plus the updated page. For example, if you make a change to a 4 kilobyte file, the entire block where this 4 kilobyte file sits must be updated and rewritten. Depending on the number of pages per block and size of the pages, you might end up writing 4 megabytes worth of data to update just one 4 kilobytes file. Actually, NVMe drives are the same flash drives as 2.5 inches SSD, which use NVMe protocol or NVMe interface instead of SAS or SATA. SATA interface provides bandwidth up to 600 megabytes second, SAS 3 approximately 1 gigabyte second, NVMe version 3 is able to show approximately 3.5 gigabytes per second. Let's start with the old boy 7.1 2K NLSAS or SATA drives. Despite of lowest performance and throughput, they have the most pleasant price per 1 terabyte. Large drive capacity allows to put 350 terabytes after RAID 6 in one 2-unit server. What would be a good solution for a Hive or backup repository? 3.5 inches form factor limits usage in 1-unit chassis, which has mostly only 4 or 6 bays. Rotating mechanical parts consume more electricity as the flash drives. But if your environment doesn't require more than 5,000 mixed IOPS and higher storage latency wouldn't be a problem, those drives in RAID 10 can perform sufficient. Next showpiece are 10K and 15K SAS drives. Higher random IOPS count and really good throughput made these drives data center standard in the past. The price per 1 terabyte of 10K and 15K SAS drives are up to 10 times higher as of 7.2K and is comparable to entry enterprise flash. 2.5 inches form factor allows high density, but opposite the maximum capacity I found on modern market is 2.4 terabytes for 10K devices and only 960 gigabytes for 15K SAS. We compare SAS spindle drives prices per terabyte and per gigabyte with flash a little bit later, and we'll see if there are any reasons purchasing 10 or 15K in 2020. Talking about flash, I would like to elaborate more on types of flash models because it has an impact on price, performance, and endurance. Current flash drives use NAND storage, the building blocks of which is the memory cell. These are the base units onto which data is written in a solid-state drive. Each memory cell accepts a certain amount of bits which are registered on the storage device as 1 or 0. The most basic type of flash drives is single level cell or SLC. SLC accepts 1 bit per memory cell. That's not a lot, but it has some advantages. Firstly, SLC are the fastest type of solid-state drives. They are also more durable and less error-prone, so they are considered more reliable than any other SSD types. But it is the most expensive flash and nowadays is used only as internal cache for other flash types like MLC or TLC. You don't find new poor SLC devices on the market. Even write-intensive flash with highest endurance uses a multi-level cells. The multi-level cells isn't particularly correct. They only store 2 bits per cell, which is not very multi. MLC are a bit slower than SLC because it takes more time to write 2 bits onto a cell than just 1. They also take a hit in durability and reliability because data is written to the NAND flash more often than as with CLC, but it's only in compare to single level cells. The modern flash devices with highest endurance, which can sustain 25 drives written per day, are based on multi-level cells. As example of such devices are Samsung SM883 or Kioxia PX05SH. Triple level cell flash write 3 bits to each cell. Nowadays, TLC are the most common type of solid-state drives. They pack more capacity than MLC drives, but sacrifice relative speed, reliability, and durability. Don't be confused, the reliability and durability is more than enough for all workloads except extreme write-heavy, like, for example, write-back cache in software-defined storage solution, or some write-intensive caching for SQL databases. Examples of TLC drives are Intel S4610 and Micron 5300 Pro. Quad level cells, or QLC, can store 4 bits of data using 16 states, which means using 16 different voltage levels. This sounds great because of high capacity and lower price per terabyte, but here are also issues. When more data is stored in cell, a single bit change entails rewriting the whole cells, and it decreases the endurance. For example, TLC memory can be rewritten approximately 5,000 times, and QLC only up to 1,000. QLC read speeds are not too different from other types of flash, but sustained write speeds can be compared to spindle drives. QLC flash is more for consumer market, and I don't find any device for data center usage. QLC is not a limit. Intel has talked about penta-level cells memory, where each cell will store 5 bits, so we can expect official announce this or next year. Based on flash types covered in previous slide, vendors offers device with more understandable names: read intensive, mixed use, and write intensive. The name is self-explaining, and I'd like to emphasize the advantages and disadvantages. Read-intensive drives like Intel S4510 or Samsung PM883 are based on TLC flash, have large capacity. In stock, I've found only 15.36 terabytes, but there are already 32 terabytes devices included in specification on vendor sites. Low price per 1 terabyte and excellent read performance makes it a best choice for environments where read operation outweighs writes. The write performance is lower only compared to mixed use and write intensive, but can be up to 500 times higher as by SAS spindle drives, especially for random write operations. Mixed use drive like Intel S4610 or Micron 5300 Max is based either on TLC or MLC flash, and it is a golden mean among other flash types with endurance and performance which can satisfy any workload except heavy write scenario. And write-intensive drives like Kioxia PX05SM are utilizing the full potential of multi-level cells flash and are supposed to be used either in heavy write scenarios or as a write cache. The outstanding performance and endurance leads to highest price per 1 terabyte and lower max drive capacity because of reserved cells. On this table, you can see average performance and price per terabyte. The IOPS count and endurance I took from official vendor specification. The price per 1 terabyte is calculated based on 3.8 terabytes and 3.2 terabytes SSDs. I used syncmate.com configurator, which provides with fair prices. By some servers vendor, cost per 1 terabyte can be much higher because of branded drives. In flash world, endurance endurance is measured either in terabytes written or drives writes per day, or DWPD. DWPD measures how many times you could overwrite the drive's entire size each day of its life. For example, suppose your drive is 1.92 terabytes and its warranty period is 5 years. If its DWPD is 3, then it means you can write 5.7 terabytes into it every single day for the next 5 years. If you multiply that out, you will get 10.5 petabytes of cumulative writes before you may need to replace it. DWPD isn't a universal number. The endurance depends also on workload. By default, vendors shows DWPD numbers mostly for random 4 kilobyte write operation. For sequential operation or larger block size, this value is higher. Maybe you have noticed that no NVMe drives are in this table, so let's move on. NVMe is a pretty young interface, and as every new technology has a variety of form factors. The first one is M2, which is commonly used in consumer devices, workstations, or as operation system storage in servers. M2 supports both NVMe and SATA protocol, so you should carefully read drive specification before buying this drive. The bandwidth is limited up to 4 NVMe lanes, what results in maximum 3.5 GB per second with PCI Express 3 protocol. U2 is most popular NVMe form factor for data center. Because of 2.5 inches physical size, it enables a higher maximum storage capacity per drive than M2 SSDs. It uses also up to 4 PCI lanes. Maximum capacity per drive on sale is 15 terabytes, and one unit server with 32 U2 slots is able to provide with incredible 490 terabytes of raw storage. With 2-unit chassis and 48 slots, the capacity reaches 737 terabytes of raw storage. By the way, U3 devices with PCI Express 4 support should come this year. Next form factor is add-on card, which in theory can utilize all 16 lanes and give 16 GB per second bandwidth. But today there are only 4 lanes drives on the market, what doesn't give any advantages in compared to U2 drives. Combining with limited PCI slots in servers, the add-on card can be recommended only as upgrade for system which doesn't support U2. The price per 1 terabyte is the highest for card PCI Express drives. Next form factors can be presented together because they have much in common. Intel ED small form factor, maybe know it as a ruler, and Samsung next generation small form factor are the newest ones with highest density per server. Both utilizes 4 PCI Express lanes, and now on the market I found only 1 unit chassis with support for this drive. So it means with max capacity of 15 terabytes per one drive, you can reach also about 490 terabytes in one server. In my personal opinion, ruleless is the form factor of the future data centers. We have already highlighted the main advantages of NVMe drives, like highest performance and lowest latency, and highest density because of small form factor. It relates more to rural devices. Certainly, such good devices cost more as SATA and SAS SSDs, but unfortunately the price is not the one's concern. Regarding local redundancy or local RAID options for NVMe, we'll talk a little bit later. Now I would like to disclose challenges in RAIN scenario. RAIN is an acronym for Redundant Array of Independent Nodes. Actually, it is what software-defined storage like VMware vSAN, Storage Spices Direct, or StarWind Virtual SAN does. The replication of NVMe drives across networks with iSCSI, Fiber Channel, or any proprietary protocols adds up network and process overhead. What kills the main advantage of NVMe drives? Low latency. As a result, the cluster will get performance and latency compared to storage based on SAS or SATA SSD array. The implementation of NVMe over Fabrics protocol can improve performance, but no software-defined solution vendor has full stack implementation of NVMe over Fabrics right now. We in StarWind have a roadmap for nearest future to do it. Okay, we have reviewed the storage media and market. Let's compare the prices. I believe that per gigabyte metrics is outdated in 2020 because data growth and drive capacity enable easily operate with per 1 terabyte prices as more informative. The winner is good old 7.2K drives, as Captain Obvious said. 32.4 USD per terabyte will satisfy every limited budget. Checking the costs for 10K and 15K SAS disks, the picture is quite ambiguous. 10K SAS is only 14% cheaper as read-intensive flash, but the performance and endurance in common workloads differs hugely. 15K SAS drives are 36% more expensive as mixed-use SATA MLC drives and 13% more expensive as NVMe read-intensive U2 drives. That's why I see reason to use 10K and 15K SAS drives only if you are adding capacity to all servers with such drives. SATA SSD has best price performance ratio, especially in small up to 10 terabytes environments. Standalone drives are rarely used in enterprise. Drives are united in RAID volumes for better performance and redundancy. Most common used RAID levels are RAID 5, which delivers capacity efficiency, sacrificing write performance and reliability. Doesn't matter how much drives are in the array, 3 or SATA, it can tolerate only one drive failure. RAID 5 consists of block level striping with distributed parity. Each write operation requires recalculation the parity, resulting low random write performance, especially with spindle disks. The array consisting of 4 drives, for example, in RAID 5, will perform as a single disk on writes. Upon failure of a single drive, subsequent reads can be calculated from the distributed parity such that no data is lost. During the rebuild after failure, all data is read from all disks, opening a chance for a second drive failure and the loss of entire array. RAID 5 can be used with flash devices because of cost efficiency less rebuild time, and small chances of second drive failure. But we don't recommend it to use it anyway with spindle drive. Doesn't matter is it NLSAS or 10 or 15 KSAS. RAID 6 consists of block level striping with double distributed parity. Double parity provides fault tolerance up to 2 failed drives, so it is one of the most redundant levels. But checksum should be calculated twice. What makes RAID 5 what makes RAID 6 the slowest one? RAID 6 is suitable for archives or backup repositories based on spindle drives. Also, it is worth using with SATA SSD where random write performance between 30 and 50,000 IOPS is acceptable. RAID 10 is a stripe of mirror and delivers excellent performance and good redundancy. Array can guaranteed lose one drive and, if you're lucky, up to half of the drives of the whole array. Because of striping and no parity calculation, the write performance achieves cumulative performance of the half of the drives in array. RAID 10 is recommended for spindle drives, but all flash environments where highest performance is an aim also can benefit from RAID 10. RAID 50 and 60 are stripes of RAID 5 or RAID 6 sets. RAID 50, for example, improves upon the performance of RAID 5, particularly during writes, and provides better fault tolerance than a single RAID 5 level does. Such arrays are worth configuring if we're talking about more than 12 or even 16 devices. You can see also RAID 15 on top of Pyramid as the most redundant one. It is a parity of mirrors and it can tolerate at least 3 drives failure. Frankly speaking, I haven't seen any implementation of it, and I'm not sure if hardware RAID controller like PERC 740 allows configure it. As you remember, one of disadvantages of NVMe drives is local redundancy challenge or concerns. Ordinary SAS or SATA hardware RAID controllers use 8 PCI Express lanes, which is enough for spindle drives or SATA solid-state drives. In case of NVMe, each device utilizes 4 lanes, so connecting more than 4 NVMe devices makes no sense. Even for 4 devices, the controller bandwidth will be a bottleneck for sequential read operations. Vendors are developing different solutions to face this challenge. I will start with Intel Virtual RAID on CPU or on chip or VROC. VROC is a hybrid solution and it uses CPU cores to calculate RAID logic. In case of large amount of NVMe drives, the CPU will be loaded heavily. In hyperconverged system, it can cause performance degradation of virtual machines. VROC is not hardware agnostic solution. It was designed for Intel flash drives and has support of some third-party vendor drives included in compatibility list. The solution is paid and delivered in 3 editions, differencing by RAID level and third-party vendor drives. Regarding VROC performance, I cannot definitely tell if it's good or not because the public test results are quite controversial. Excellent read results with RAID 10 and RAID 0 and relative poor random and sequential write in RAID 10 and RAID 5. The next option is software RAID like storage spaces, Linux RAID, etc. Software RAID utilizes CPU heavily and gives slow performance with parity or RAID 5, even lower as SATA SSD RAID 5 on hardware RAID controllers. Software RAID makes sense to use not only for RAID 1 or RAID 10. The next one is hardware RAID based on Marvell or Broadcom chips. The both supports up to 4 NVMe drives, and because of using only 8 PCI lanes, the max throughput varies from 4 to 7 gigabytes per second. The high point SSD 7120 aims more consumer market. RAIN or software-defined storage solution, as covered before, doesn't provide a local redundancy, so you cannot deploy it only with one node, and has network and processing overhead. As conclusion, correct designed array of SATA or SAS SSD devices provides the comparable performance right now. As for me, I'm watching Intel's VROG and hope the right performance will be improved in the next releases. Based on discussed topics, I would like to share our recommendations. 7.2K NLSAS HDDs in RAID 6 for archive data or backups repositories. 7.2K NLSAS spindle drives in RAID 10 for environments which requires much capacity and low random operation performance, up to mixed 5000 IOPS. Read intensive SATA SSD in RAID 5 or 6 for environments with moderate write performance requirements and capacity flexibility. From 50,000 till 100,000 mix IOPS can be delivered with read intensive SATA SSD. Mixed used SATA SSD in RAID 5 or in RAID 6 for high performing read-write balance environment where up to 250,000 mix IOPS required. Mixed use or write intensive SAS SSD in RAID 10 for the highest performance where 500,000 IOPS is not a limit. And NVMe without RAID for outstanding performance and lowest latency where redundancy can be sacrificed. That's all regarding the theme of the webinar. And now, taking into account flash prices decrease, StarWind decided to redesign hyperconverged appliances product line and goes all flash to bring your applications the ultimate glory of both capacity utilization and climatic performance while maintaining the benefits of evidently decreased total cost of ownership and increased return of investment. Starting March 2020, HCA includes 3 new model lines. Value flash appliances are the option with the best price per gigabyte value. These models are built to provide high storage capacity and moderate compute power for capacity-hungry applications. Read-intensive solid-state drives are used here. Next one is capacity flash appliances, which utilizes automated storage tiering of read-intensive and mixed-use drives to handle performance-intensive workloads in a cost-efficient manner. It provides an excellent balance between performance and costs. These models are built to deliver high storage capacity and great performance. And last but not the least, performance flash appliances powered by mixed drives use only to deliver the best performance. More information and basic specification of new generation hyperconverged appliances you can find on StarWind website, and certainly do not hesitate to contact our sales teams for any questions. Now it's good time to ask questions, if any. Okay, I see a question. Just a moment. The question is, will the recording be made available? Yes, it will be, but I think end of next week. Next question is, do you see an advantage of using SAS SSDs over SATA SSDs? If we don't take care of prices, certainly SAS SSDs are performing better. But if your environment doesn't require more than 250,000 IOPS, SATA SSD will be the best solution for you. You may also say that SAS protocol ensures data integrity, and using SATA protocol, some bits of information can be lost between motherboard or RAID controller and the drive itself. Yes, it's true, but if we're talking about drives which are in RAID, the most RAID controllers perform data integrity check and can mitigate such issue. So SAS SSDs can be used only in specific cases, as I mentioned, for really high performance. And as far as I know, it's really hard to find write-intensive SATA SSD. Only write-intensive SAS SSD are on the market. Okay, we have a new question. Storage needed for video surveillance purpose. It's a hard question without knowing the information. For example, how many cameras, what is the bandwidth or throughput of each camera. Actually, the video surveillance systems do pseudo-sequential writes. And in small environments, nearline SAS HDDs will be enough for it. But if we're talking about, for example, 1,000 cameras, maybe you should look at a hybrid storage solution with auto-tiering. For example, all writes goes on mixed-use SATA SSD or even SAS SSD, and then flashed to read-intensive or SSDs or HDDs. So if you are going to build a video surveillance system based on StarWind Virtual SAN high availability, so our engineers will help you to select the proper underlying storage. The next question, if SSD storage trays really reach their lifetime span, what happens to drive? Will the drive stop working, or would it give an alert to the RAID controller or to the room environment? SSD drives supports smart parameters, and each SSD drives has reserved cells. So if, for example, we are talking about redundancy for, let's say, 3.8 terabytes capacity drives, it means that really this drive has cells for 5 or even more terabytes of data. If some of the cells is broken, then the microcontroller of drive replace the addressing of the cells with the reserved one. The count of free reserved cells can be read from the smart parameters. And certainly, if there are more reserved cells left, this drive will continue to work without any problems. Unfortunately, as SSD technology is also not very old, there are too many statistics. I mean, if such drives can work for 8 or 10 years. So a month ago, a cloud storage service provider, Backblaze, shared the results of failed drives, and the statistic was that 2% of SSD drives failed in the last year in their environment. But as far as I remember, we are talking about 5 or 7,000 SSD drives. So I'm not sure. I don't want to provide the wrong information. So if you are interested in this report, you can easily find it in internet. Okay. If there are no more questions, I thank you again for attention. Have a nice day, nice evening. Goodbye, and hear you on next webinar.